There are patterns in nature that repeat with clockwork precision. The rotation of Earth, completing one full turn every 23 hours, 56 minutes, and 4 seconds. The orbit of the Moon, circling our planet in its ancient gravitational dance. The pulse of a neutron star, sweeping its beam across the cosmos like a lighthouse in the dark, flashing with regularity measured in milliseconds. These are the rhythms we understand, the cadences written into the fundamental laws of physics, predictable, mathematical, comfortable in their regularity. They emerge from conservation of angular momentum, from the inexorable pull of gravity, from the quantum mechanical properties of matter compressed to unimaginable density. But on July 1st, 2025, astronomers discovered something repeating with a precision that shouldn't exist. Not from a star whose pulsations we can model with equations describing nuclear fusion and stellar oscillations. Not from a planet whose orbital period derives from Newton's laws applied to masses and distances we can measure. From a visitor, an object that traveled through the void between stars for billions of years before arriving in our cosmic neighborhood, carrying within it mysteries from stellar systems we may never see. And this visitor, designated 3I Atlas, the third confirmed interstellar object ever detected by human instruments, is pulsing every 16.16 hours like a heartbeat echoing across the solar system, a signal so precise, so regular, so mathematically perfect that it has forced scientists to ask a question they never expected to confront in their careers, a question that makes some uncomfortable and fills others with excitement. What if the light we're seeing isn't coming from spinning ice and rock? What if we're watching something breathe? Before we go on, comment your city name so I'll know from which corner of Earth and which edge of the universe my voice has reached you. Because tonight, we're going to trace a mystery that reaches from the automated telescopes of Chile, scanning the southern sky night after night in search of threats and discoveries, to the most sensitive instruments humanity has ever built, machines capable of detecting photons that travel across light years of interstellar space. We're going to examine data that doesn't make sense, observations that contradict what we think we know about comets, measurements that challenge our understanding of how natural objects behave. And we're going to explore a pattern that repeats with such mathematical perfection, such unwavering regularity, that it forces us to consider possibilities we'd rather not imagine, possibilities that blur the line between natural phenomenon and something else entirely. Stay with me, because what we're about to explore goes far beyond a simple comet tumbling through space. By the time we reach the end, you'll understand why the fraction of light matters more than you ever thought possible. Why a seemingly simple calculation about how much brightness comes from the nucleus versus the coma reveals a paradox that conventional physics struggles to explain. You'll understand why jets of gas and dust might be revealing something extraordinary, why their behavior doesn't match what we expect from thermal sublimation driven by solar heating. And you'll understand why 16.16 hours might be the most important number in astronomical observation since the discovery of pulsars, why that specific periodicity carries implications that reach far beyond the properties of a single object. Let me take you back to the beginning, to the moment when routine became remarkable, when another night of automated sky surveys transformed into the opening chapter of a mystery that continues to deepen with each new observation. The Atlas Survey Telescope in Chile operates with mechanical precision, a marvel of engineering designed to protect Earth from cosmic threats. Night after night, its automated systems photograph the sky, capturing images of millions of stars, comparing new images against archival data with sophisticated algorithms, searching for anything that moves, anything that changes, anything that doesn't belong to the static background of distant stars. The primary mission is planetary defense, finding asteroids that might pose collision risks, tracking their orbits, providing early warning of potential impacts. It's unglamorous work most of the time. The vast majority of objects detected are known asteroids following predictable paths, no threat, no surprise, just another data point confirming that our models of solar system dynamics are accurate. On July 1st, 2025, during what should have been a routine observation run, the software flagged an object, faint, barely magnitude 20, requiring exposure times measured in minutes to capture enough photons for detection, a tiny point of light drifting slowly against the stellar backdrop. To put magnitude 20 inches perspective, that's roughly 4 million times fainter than the dimmest star visible to the naked eye on a perfectly dark night. You'd need a telescope with a mirror at least 8 inches in diameter just to see it at all, and even then it would appear as nothing more than a barely perceptible dot, indistinguishable from the countless background stars except for one crucial characteristic: it moved. The initial classification was unremarkable. The motion was slow, consistent with an object in the outer solar system, far from the sun, where orbital velocities drop and objects drift lazily through space like ships becalmed in cosmic doldrums. Just another distant comet, another chunk of ice and rock following its appointed path through the outer solar system, probably in a long elliptical orbit that carries it from the inner regions near Mars out to distances beyond Neptune, taking decades or centuries to complete one circuit around the sun. Objects like this are discovered regularly. They're cataloged, their orbits calculated, and unless they pose some threat or display unusual activity, they fade into the background of astronomical knowledge. One more entry in databases containing millions of solar system objects. But within hours, as observatories around the world turned their instruments toward this new discovery, as trajectory calculations refined and orbital elements crystallized, as more observations accumulated and the mathematical models describing the object's path through space became increasingly precise, the truth emerged with stunning clarity. This wasn't just another comet. The orbit was wrong. Not slightly off, not marginally unusual, but fundamentally, undeniably wrong. Hyperbolic, not elliptical. This object wasn't bound to our sun. The mathematical signature was unmistakable. The orbital energy was positive, not negative. The eccentricity exceeded 1. This object was moving too fast to be captured by our sun's gravity, carrying with it sufficient kinetic energy to escape the solar system entirely, to return to the interstellar void from which it came. It came from somewhere else, from another star system, from a planetary system forming around a sun we cannot see, ejected by gravitational interactions we can only imagine, cast into the darkness between stars billions of years ago, when our own solar system was young or perhaps before it even existed. The astronomical community designated it 3I Atlas, following the naming convention that reserves the letter I for interstellar, marking it as the third confirmed interstellar object ever detected by human instruments, a member of an exclusive club that until 2017 contained 0 members, and now, in 2025, contains 3, each one unique, each one strange in its own way, each one forcing us to reconsider what we think we know about the contents of interstellar space. And suddenly, what seemed routine became extraordinary. Observatories that might have given this object a cursory glance before moving on to other targets suddenly prioritized it. Observation time on major telescopes, normally allocated months in advance through competitive proposals, was hastily rescheduled. Astronomers who study interstellar objects, a field that barely existed a decade ago, mobilize for an intensive observation campaign. Because opportunities like this are rare. Interstellar visitors pass through our solar system quickly. They don't return. You get one chance to study them, one window of observation before they fade back into the darkness. And if you miss that window, the opportunity is gone forever. Yet, even as excitement built around this cosmic visitor, even as telescopes coordinated observation campaigns and scientists prepared analysis protocols, drafting plans for spectroscopic studies to measure chemical composition, photometric monitoring to track brightness variations, astrometric measurements to refine the trajectory to higher precision, something else was happening. Something subtle, something that would take weeks to fully recognize, hidden in the data accumulating across multiple observatories, visible only when someone took the time to compile all the brightness measurements and search for patterns. The object was changing brightness. Not dramatically, not with the explosive outbursts typical of active comets approaching the sun, where volatile ices suddenly vaporize in response to solar heating, creating surges in activity that can increase brightness by factors of 10 or 100 in a matter of hours. The changes were more subtle than that, but they weren't random fluctuations driven by noise in the measurements or variations in atmospheric seeing conditions. They were rhythmic, systematic, with a regularity that demanded explanation, a pattern that repeated too consistently to be coincidence. Observers began accumulating photometric data, a painstaking process that involves measuring the intensity of light coming from 3i Atlas across multiple nights, accounting for variables like atmospheric extinction, the brightness of the background sky, the calibration of the instruments, all factors that can introduce systematic errors if not handled carefully. The measurements showed variation. Sometimes the object appeared brighter, sometimes dimmer, and the changes weren't random scatter around a mean value. They followed a pattern, a cycle. When astronomers performed period analysis on the light curve data, when they applied Fourier transforms and Lomskargo periodograms and other mathematical techniques designed to search for repeating signals buried in noisy measurements, they found it. A periodicity of 16.16 hours. Not approximately 16 hours, not roughly half a day, not something you could round to a convenient number. Exactly 16.16 hours, repeating with precision, that made the measurements undeniable. The period was present in data from multiple independent observatories. It showed up in observations taken with different telescopes, different cameras, different filter sets. It persisted across multiple nights, across weeks of monitoring. This wasn't an artifact of a single instrument or a fluke of one night's data. This was real. Something about 3i Atlas was causing its brightness to vary on a precise 16.16 hour cycle, and that something demanded explanation. The amplitude of this variation was significant. Tens of percent, not the subtle variations of a few percent you might attribute to instrumental effects or minor changes in viewing geometry. The object would brighten substantially, increasing in luminosity by 20, 30, sometimes even 40% above its minimum brightness, then dim again, then brighten once more, cycling through this pattern every 16.16 hours with mechanical regularity. Plot the data on a graph with time on the horizontal axis and brightness on the vertical, and you see a wave, a sinusoidal variation that repeats like the heartbeat. It resembles each peak separated from the next by exactly 16.16 hours, each trough arriving on schedule, predictable as clockwork. For scientists trained in cometary of physics, specialists who have spent years or decades studying how comets behave, this seemed to have an obvious explanation. Cometary nuclei are rarely spherical. They're irregular, lumpy, often elongated like cosmic potatoes tumbling through space, shaped by the collisions that created them and the outgassing that erodes their surfaces. As they rotate, different surface areas reflect sunlight toward Earth. When the long axis points toward us, when we're looking at the broad side of an elongated object, we see more reflected light and the object appears brighter. When the narrow end faces us, when we're looking at the object end on, less light reaches our instruments and the object dims. The periodicity simply reveals the rotation period, the time it takes for the nucleus to complete one full spin. This is standard textbook astronomy. We've observed rotational light curves from countless asteroids and comets. We use them to infer shapes, to map out surface features, to detect binary objects that eclipse each other as they orbit around their common center of mass. The physics is straightforward. The mathematics is well established. There's nothing mysterious about a rotating irregular object producing periodic brightness variations. It's one of the most basic phenomena in observational astronomy. The observers who first reported this variability calculated that to produce brightness changes of this magnitude, variations of tens of percent from maximum to minimum, the nucleus of 3I Atlas would need to have an axis ratio of about 0.8. Picture an object that's slightly elongated, like a football that's not quite fully inflated, like an egg with a ratio of long axis to short axis around 1.25 to 1, spinning end over end through space. This seemed entirely reasonable, entirely natural, entirely consistent with what we know about cometary nuclei throughout the solar system. Many comets have elongated shapes. Some are even more extreme, with axis ratios of 2 to 1 or 3 to 1, tumbling irregular chunks that produce light curves with even larger amplitude variations. The mystery appeared solved before it even began. 3I Atlas is an interstellar comet with an elongated nucleus rotating every 16.16 hours. The brightness variations are simply the natural consequence of that rotation changing which cross-section we see. File it away, move on to other questions, like the chemical composition, the size of the nucleus, the density of the coma, the trajectory refinements. The rotation period is explained, case closed. But then the Hubble Space Telescope looked closer, and everything changed. On July 21st, 2025, after weeks of scheduling negotiations and target of opportunity observations that bumped other planned science to later dates, Hubble captured an image of 3I Atlas at wavelengths spanning the visible spectrum. The resolution was extraordinary, the detail unprecedented for an interstellar visitor. Hubble's imaging capabilities, even aging as the telescope enters its fourth decade of operation, still surpass what most ground-based observatories can achieve. The sharp focus, the lack of atmospheric distortion, the sensitivity to faint details, all combine to produce an image that revealed structure invisible in ground-based observations. And what Hubble revealed forced a fundamental reconsideration of everything astronomers thought they understood about this object's brightness variations. Because Hubble showed with clarity that left no room for interpretation that most of the light we see from 3I Atlas, the light that varies with that precise 16.16-hour period, doesn't come from the nucleus at all. It comes from the coma, the glowing cloud of gas and dust surrounding the solid core, extending outward for hundreds of thousands of kilometers in all directions, dominating the visual appearance of the object when viewed through any telescope. Think about what that means. When you look at 3I Atlas through a telescope, whether it's a small amateur instrument or a professional research facility, you're not seeing a distinct solid object like viewing the moon or Mars, where the surface reflects sunlight and you can make out craters and Maria and other features that delineate the solid body. You're seeing a fuzzy patch of light, a luminous halo extending hundreds of thousands of kilometers into space, larger than the distance from Earth to the moon, larger than any individual planet in our solar system, a vast diffuse cloud glowing because it's filled with microscopic dust particles and molecules that scatter sunlight in all directions. The coma is transparent, or at least translucent. You can see through it, though it becomes optically thick, near the center where the density of particles is highest. Somewhere in the center of that glowing cloud sits the actual nucleus, the solid chunk of ice and rock that spawned this entire structure, the source from which all this gas and dust originated when volatile ices began sublimating as the object approached the sun and solar heating penetrated the frozen surface. But the nucleus itself, the actual solid body, contributes only a tiny fraction of the total light we observe. Most of what we see is scattered sunlight from the coma. The Hubble image allowed researchers to make critical measurements that were impossible with ground-based observations. They identified the brightest pixel in the image, the point where light intensity peaks, the location where the solid nucleus presumably resides, though even Hubble cannot resolve an object a few kilometers across at the distance where 3I Atlas was located when the image was taken. And they calculated what fraction of the total light originates from that central point versus the extended coma surrounding it. This requires careful analysis, integrating the brightness across the entire image, subtracting background sky light, accounting for the point spread function of the telescope that smears light from point sources, all technical details that make the difference between a rough estimate and a precise measurement. The results were striking, disturbing even. If all the observed light came from reflected sunlight off the solid surface of the nucleus, if there were no coma at all and we were seeing only the rocky icy core, the effective radius would need to be approximately 10 kilometers in visible light. At a wavelength of 1 micrometer in the near-infrared where the measurements were made, the effective radius would be about 23 kilometers, assuming a typical cometary albedo of 4 to 5%, meaning the surface reflects 4 to 5% of the incident sunlight and absorbs the rest. But that's the effective radius, a mathematical construct, the size the nucleus would need to be if it were reflecting all the light we observe. The actual radius, the real physical size of the solid core, must be much smaller, because most of the light isn't coming from the nucleus, it's coming from the coma. When scientists analyzed the Hubble data more carefully, when they looked at the brightness profile, how intensity falls off with distance from the center, they could place an upper limit on the actual nucleus size. The analysis suggested an actual radius of approximately 2.8 kilometers, maybe smaller, maybe marginally larger, but certainly in that range. That's dramatically smaller than the effective radius suggested by the total brightness, smaller by a factor of 8 or more. Here's where the mathematics become disturbing, where the numbers reveal a paradox that conventional explanations struggle to resolve. The fraction of light reflected by the nucleus relative to the total light from the coma plus nucleus scales as surface area. Surface area scales as radius squared. This is basic geometry. A sphere with radius r has surface area 4 pi r squared. If you have two spheres with radii r1 and r2, the ratio of their surface areas is r1, r2 squared. So if the effective radius is 23 kilometers, but the actual radius is only 2.8 kilometers, the fraction of light coming from the nucleus is approximately the ratio of those areas, 2.8 squared divided by 23 squared. Calculate that. 8 squared equals 7.84. 23 squared equals 529. The ratio is 7.84 divided by 529 equals 0.0148, or about 1.5%. At a wavelength of 1 micrometer, the solid nucleus of 3I Atlas reflects less than 2% of the total light we observe. Let that sink in for a moment. Let the implications of that number settle into your mind. Less than 2%, fewer than 2 photons out of every 100 that reach our telescopes from 3I Atlas originate from reflected sunlight off the solid nucleus. The overwhelming majority of the light, more than 98%, originates from the coma, from the cloud of sublimated gas and microscopic dust particles scattering sunlight in all directions, from material that has been ejected from the surface and now surrounds the nucleus in an enormous glowing envelope. And yet the total light, the combined glow from coma and nucleus together, varies by tens of percent over that precise 16.16-hour cycle. The brightness changes by 20, 30, 40% from maximum to minimum. If the nucleus itself contributes less than 2% of the total light, how can its rotation possibly cause brightness variations of 20, 30, even 40% in the total signal? How can something that accounts for only 1.5% of the observed light modulate the total brightness by amounts 20 times larger than its own contribution? The numbers don't work. The geometry doesn't work. Even if the nucleus were perfectly elongated, even if it varied from maximum to minimum cross-section as it rotated, even if it changed from presenting its broadside to presenting its narrow end, the amplitude of brightness variation it could produce would be limited by the fraction of total light it contributes. If the nucleus only accounts for 1.5% of the observed light, then its rotation can at most cause variations of a few percent, perhaps 3 or 4%, if the shape is extremely elongated. Not tens of percent, not the 20 to 40% variations we actually observe. Yet we observe variations of tens of percent. The measurements are unambiguous. Multiple independent observers see the same effect. The periodicity is confirmed. The amplitude is confirmed. The data is real. Something is varying. Something is causing the total brightness to cycle by large amounts every 16.16 hours. But it's not the rotating nucleus. The nucleus is too small, contributes too little light to explain the magnitude of the effect. Something else is varying. Something much brighter. Something that dominates the total luminosity. Something that accounts for the majority of the photons reaching our detectors. Something that isn't the rotating solid core. Something in the coma is pulsing. This is the moment when coincidence transforms into mystery. This is where a simple observation becomes a puzzle that challenges our understanding. Because if the coma is producing the brightness variations, if that enormous glowing cloud extending hundreds of thousands of kilometers from the nucleus is somehow cycling through bright and dim phases every 16.16 hours, then we need an entirely different explanation. We need a mechanism that makes the coma itself brighten and fade with clockwork precision. We need a process that operates on scales vastly larger than the nucleus, a process that can modulate the scattering of sunlight by dust and gas across volumes of space measured in hundreds of thousands of cubic kilometers. And that mechanism must somehow be synchronized with the 16.16-hour period. Not approximately synchronized, exactly synchronized. Whatever is causing the coma to pulse is tied to that specific period with precision that implies a fundamental connection. Over the past several months, multiple telescopes have captured images of 3I Atlas showing detailed structure in the coma, not a smooth, featureless cloud like you might expect from isotropic sublimation, where gas and dust are released uniformly in all directions. Instead, the images show organized features, structure, asymmetry, jets, streams of material emanating from the nucleus, pointing in specific directions, extending for vast distances into space, creating bright filaments against the background glow of the more diffuse coma. Some of these jets appear to point toward the sun, creating what astronomers call anti-tail structures. Others extend in different directions, creating complex asymmetric patterns that shift and evolve as the object moves through its orbit, as viewing geometry changes, as the rotation of the nucleus brings different active regions into view. Jets are common in comets. We've observed them in hundreds of objects. They're a natural consequence of how cometary sublimation works. As a cometary nucleus approaches the sun, as solar radiation heats the frozen surface, volatile compounds sublimate directly from solid to gas, skipping the liquid phase because the vapor pressure of ice and vacuum is too low to maintain liquid water or liquid carbon dioxide. Water ice, carbon dioxide ice, methane, ammonia, all vaporizing and expanding into the vacuum of space, accelerating outward as the pressure of sublimation drives the gas away from the surface. This gas carries with it microscopic dust particles, tiny grains of rock and carbonaceous material that were mixed with the ice when the comet formed billions of years ago. The particles are lifted off the surface by the expanding gas, entrained in the flow, accelerated to velocities of hundreds of meters per second as they ride the gas stream away from the nucleus. These dust particles are what make comets visible. Pure gas is transparent, invisible, unless it fluoresces under ultraviolet radiation from the sun. But dust particles scatter sunlight. They create the visible coma, the tail, the jets, all the structures we associate with active comets. The jets trace the locations where sublimation is most intense, where cracks or fresh ice expose material that can readily vaporize under solar heating, where the surface hasn't yet developed an insulating layer of non-volatile dust that would block sublimation from deeper layers. But here's what makes 3I Atlas different from typical comets. Here's where the comparison to other objects breaks down, and we enter territory where standard models struggle to explain the observations. If the mass loss in these jets is pulsed periodically, if the rate of sublimation varies in a systematic cycle, rather than being continuous or randomly fluctuating, then the resulting coma would display periodic variability in its scattering of sunlight. More mass ejected per unit time means more particles in the coma at any given moment, which means more surfaces available to scatter sunlight, which means the object appears brighter. Less mass ejected means fewer particles, less scattering, dimmer appearance. If this pulsing occurs on a 16.16 6-hour cycle, if the jets turn on and off, or at least vary dramatically in intensity on that time scale, you'd observe exactly what we see. Brightness variations of tens of percent, synchronized with extraordinary precision, driven not by the rotation of the solid nucleus, but by periodic changes in the activity level of the jets. In the context of a natural comet, this could arise from a specific geometric configuration. Imagine a large pocket of volatile ice, perhaps water ice or carbon dioxide ice or some mixture of both, located on one particular region of the nucleus surface. Perhaps it's a large fresh crater that exposed pristine ice beneath a dust mantle. Perhaps it's a cliff face where the ice is directly exposed to sunlight without any insulating layer. Perhaps it's a region enriched in particularly volatile compounds that sublimate readily even at relatively low temperatures. As the nucleus rotates, as it spins on its axis with a period of 16.16 hours, this pocket of ice moves in and out of sunlight. When it faces the sun, when it rotates into direct solar illumination, solar radiation heats it intensely. The surface temperature rises. The sublimation rate increases exponentially with temperature, according to the Clausius-Clapeyron equation. A powerful jet erupts, spewing gas and dust into space at velocities determined by the temperature and molecular weight of the sublimating species. For water vapor at typical cometary temperatures near the freezing point, velocities are a few hundred meters per second. For carbon dioxide, which is lighter, velocities can reach 500 or 600 meters per second. The jet is bright, dense with particles, clearly visible in images. The coma brightens dramatically as this fresh material scatters sunlight. But as the nucleus continues rotating, as the 16.16-hour period progresses, the ice pocket moves away from direct sunlight. Perhaps it rotates to the terminator, the boundary between day and night on the nucleus, where solar heating drops off. Perhaps it rotates fully onto the night side, the hemisphere facing away from the sun, where temperatures plummet and sublimation essentially ceases. The temperature of the ice drops. The sublimation rate decreases. The jet weakens. Less fresh material is injected into the coma. The existing dust and gas continue their outward motion, but they're no longer being replenished at the same rate. The material begins to disperse, spreading outward, diluting, as it expands into larger volumes of space. The density of particles drops. The brightness decreases. The coma dims. Then, 6 hours later, the rotation brings the ice pocket back around to face the sun again. The solar heating resumes. The surface temperature rises. The sublimation rate increases. The jet reignites, roaring back to life, injecting a fresh pulse of gas and dust into the coma. The brightness surges upward. The cycle repeats. A heartbeat. This is not merely metaphorical language. The pattern genuinely resembles a biological heartbeat, the rhythmic pumping of a heart driving pulses of blood through arteries and capillaries. Each rotation period delivers a fresh pulse of material into the coma, a burst of gas and dust that temporarily boosts its brightness before the effect fades, only to be renewed when the next cycle begins. The gas and dust serve the role of blood in this cosmic analogy, flowing out from a central source, distributed through an extended structure, keeping the entire system luminous and visible, pulsing rhythmically at intervals determined by the rotation period of the source. The physics appears straightforward. Sublimation rates depend on temperature, which depends on solar illumination, which depends on which part of the nucleus faces the sun at any given moment. If the nucleus has an asymmetric distribution of volatile ice, if certain regions are particularly rich in sublimatable material, while others are depleted or covered by non-volatile dust mantles that block sublimation from deeper layers, then rotation will naturally produce periodic variation in activity level. This happens with comets in our own solar system. We've observed it directly with spacecraft flybys. The Rosetta mission that orbited Comet 67P, Churyumov-Gerasimenko watched jets turn on and off. The Deep Impact mission that crashed a probe into Comet Tempel, one observed how activity varies with rotation. Jets are not continuously active. They pulse, they vary. The underlying cause is rotation, bringing different surface regions into and out of sunlight. But there's a critical constraint that must be considered, a piece of physics that determines whether this mechanism can actually explain what we observe. The outflow velocity of sublimated material. When ice vaporizes on a cometary nucleus, the resulting gas expands into the near vacuum of space. There's essentially no atmospheric pressure to push against, so the gas accelerates outward, driven by its own pressure gradient. The thermal velocity of the gas molecules depends on temperature and molecular weight. For water vapor near the freezing point, typical velocities are a few hundred meters per second. Observations from the James Webb Space Telescope reported in detailed spectroscopic analysis of 3I Atlas published in referee journals and made available through the Astrophysics Data System suggest an outflow velocity of approximately 440 meters per second for the sublimated volatiles. This is slightly higher than typical water vapor velocities, which might suggest the gas is hotter than usual, or perhaps dominated by lighter molecules like carbon dioxide, which would achieve higher velocities at the same temperature. At 440 meters per second, how far can material travel in 16.16 hours? The calculation is straightforward. Distance equals velocity multiplied by time. We have the velocity, 440 meters per second. We need to convert 16.16 hours into seconds to match the units. 1 hour contains 3,600 seconds. So 16.16 hours equals 16.16 times 3,600, which equals 58,176 seconds. Now multiply 440 meters per second times 58,176 seconds equals approximately 25,597,440 meters, or roughly 25,600 kilometers. That's the maximum distance that sublimated material ejected at the beginning of one rotation cycle could reach before the next cycle begins. It's substantial. To put it in perspective, 25,600 kilometers is roughly twice the diameter of Earth. It's about 6% of the distance from Earth to the Moon. If you could see this distance marked out in space, if you could watch material travel this far, you'd be witnessing motion on a scale larger than any terrestrial structure, larger than continents, larger than our entire planet. If a jet erupts when the ice pocket rotates to face the sun, the material from that jet traveling at 440 meters per second can travel more than 25,000 kilometers outward before the nucleus completes one rotation and the next pulse begins. This creates structure in the coma, layered structure like the ripples that spread from a stone dropped in water. Each pulse adds a new wave of material, a new shell of gas and dust expanding outward at 440 meters per second. This new shell overlaps with the remnants of previous pulses that have already spread further outward, creating a nested series of expanding shells, each one representing a different rotation cycle, each one containing dust ejected at a different time. If we could watch this process in real time, if we had time-lapse imaging showing the evolution of the coma structure over multiple rotation periods, we should observe a breathing pattern. The inner coma brightens as a fresh jet erupts, as new material floods into the volume immediately surrounding the nucleus. The bright region expands outward at 440 meters per second, creating an expanding shell that we could track if our images had sufficient spatial and temporal resolution. Behind it, the brightness fades as the material spreads into larger volumes. As the density drops, as fewer particles per unit volume mean less total scattering. Then the next pulse arrives, injecting fresh material into the inner coma, and the cycle repeats. The total brightness of the entire coma, integrated across all this structure, would vary periodically. It would be bright when a fresh pulse is actively erupting and filling the inner coma with dense material. It would be dimmer during the intervals between pulses when no fresh material is being added and the existing gas and dust continue to expand outward, diluting as they go. The amplitude of brightness variation would depend on the relative strength of the pulsed emission compared to any continuous background emission, on how much material is ejected per pulse versus how much leaks out continuously from other regions of the nucleus that maintain some level of activity regardless of solar illumination. This mechanism is entirely natural. It requires no exotic physics, no unusual chemistry, nothing that violates our understanding of how comets work or how sublimation proceeds. It simply requires two conditions to be met. First, an asymmetric distribution of volatile ice on the nucleus, with certain regions being far more active than others. Second, a rotation period that brings the most active region into sunlight at regular intervals. Both of these conditions are common in comets. Many comets have highly asymmetric activity patterns. We've seen comets where a single jet produces the majority of the total mass loss. We've seen rotating nuclei with all different rotation periods, from a few hours for small objects with rapid spins to several days for larger objects rotating more slowly. The 16.16-hour period tells us the rotation rate of the nucleus is rotating slightly faster than 1 revolution per day, completing a bit more than 1 full spin in the time Earth rotates once. This is a perfectly reasonable rotation period for a cometary nucleus, a few kilometers in diameter. The amplitude of brightness variation tells us how much more active the nucleus is when the ice pocket faces the sun compared to when it doesn't. How much the jets dominate the total emission versus any diffuse background activity. Everything fits within the framework of standard cometary science. The physics makes sense. The numbers work out. The explanation is plausible, except for one disturbing detail that undermines the entire elegant explanation. No one has actually observed this heartbeat pattern directly. Think about what I mean by that. The evidence for periodic pulsing comes from photometric measurements from tracking the total brightness of 3I Atlas over multiple nights and detecting the 16.16-hour cycle in that integrated light. Observers point their telescopes at the object, measure how bright it appears, record the time of the observation, and accumulate measurements across many nights. When you plot all those brightness measurements against time, when you search for periodic signals in the data using mathematical techniques designed to find repeating patterns, you discover the 16.16-hour cycle. It's there in the data, undeniable, confirmed by multiple independent groups using different telescopes. But that's total integrated brightness. That's the sum of all the light coming from the entire object, nucleus plus coma, integrated across the entire volume, visible in the telescope's field of view. It doesn't tell you what part of the object is varying. It doesn't show you which structures are brightening and which are fading. It doesn't reveal the spatial distribution of the brightness changes. To confirm the mechanism I just described, to verify that the jets are truly pulsing in the manner the heartbeat model predicts, we would need something different. We would need a series of well-calibrated snapshots of the coma over several days, high-resolution images taken at intervals shorter than the 16.16-hour period, showing how the structure of the coma evolves with time. We would need time-lapse imaging showing the jets brightening and fading, showing where the brightness increases occur, showing material expanding outward in successive pulses like ripples spreading from a splash. We would need to see the active region, the source of the main jet, rotating around the nucleus, moving from the day side to the night side and back again, with the brightness of the jet varying accordingly. We would need to actually see the heartbeat in action, not just infer it from total brightness measurements. We would need to watch the coma breathe. As of now, as this script is being recorded, no such systematic study has been published in the scientific literature. Searches through the major astronomical databases, the Astrophysics Data System that catalogs all published papers in astronomy, journals like Nature and Science and the Astrophysical Journal, reveal papers about 3I Atlas discussing its discovery, its trajectory, its chemical composition, but no published time series imaging study showing the evolution of coma structure correlated with the 16.16-hour brightness variations. The Hubble image from July 21st is a beautiful snapshot, a single moment frozen in time. It shows the jets clearly. It shows the coma structure in exquisite detail. It provides critical information about the nucleus size and the relative contribution of nucleus versus coma to the total light. But it's one frame, one image. It doesn't show evolution. It doesn't reveal the temporal sequence of brightening and fading that would confirm the pulsing jet hypothesis. This gap in the observational record is significant. It's not just a minor detail, it's a critical missing piece of evidence. Because without direct observation of the heartbeat pattern, without watching the coma pulse in synchronization with the 16.16-hour period, without seeing the jets brighten and fade, and correlating those changes with the rotation of the nucleus and the solar illumination geometry, we cannot definitively rule out alternative explanations. And some of those alternatives, some of the other ways you could produce precise periodic brightness variations in an object's coma, are far less comfortable than natural sublimation cycles driven by rotation and solar heating. Consider what would be required for a technological explanation. If 3I Atlas is not a natural comet, not merely ice and rock shaped by random processes and following the dictates of orbital mechanics, but something else, something designed, something engineered, then the periodic brightness variations could arise from entirely different mechanisms. A directed emission system pulsing at regular intervals according to programming established when the object was constructed perhaps billions of years ago. Thrusters firing in a programmed sequence for trajectory correction, for maintaining orientation, for course adjustments as the object navigates through interstellar space and approaches its target star system. A rotating beacon sweeping a beam of light or plasma across space, creating the appearance of periodic brightening as the beam aligns with Earth's line of sight every 16.16 hours, like a lighthouse whose flash you see only when the rotating beam points in your direction. For a technological object, for something built rather than formed, the direction of the pulsing jets would not necessarily correlate with the sun. This is the critical distinction. Natural jets point in directions determined by the location of volatile ice on the nucleus surface and the angle of solar illumination. Solar heating is the energy source driving the sublimation. The geometry of solar illumination controls where and when sublimation occurs. Jets should point away from active regions on the surface, and active regions should be those that receive strong solar heating. There should be a clear correlation between jet direction and solar direction, but engineered systems could pulse in any direction. The orientation of the jets relative to the sun could be arbitrary, determined by the placement of emission nozzles or thruster ports, by the design of the propulsion system, by the mission requirements that guided the object's construction. The jets might maintain fixed orientations in space while the object rotates, pointing toward specific targets, toward the direction of travel, toward the home system from which the object was launched, toward Earth. If Earth is the target of observation or communication, they might show patterns completely inconsistent with thermal sublimation driven by solar heating. A movie showing the periodic brightening of the jets around 3I Atlas over several days could reveal which scenario is correct. Watch the jets carefully. Do they turn on when a particular region of the nucleus rotates into sunlight? Do they turn off when that region rotates into shadow? Does the pattern track the sun's position relative to the nucleus, maintaining the relationship you'd expect if solar heating is the driving force? If yes, if the correlation is clear, if the jets brighten when illuminated and fade when shadowed, then natural. The mechanism is sublimation. The periodicity is rotation. The object is a comet. If the jets pulse according to some other schedule, if they ignore solar geometry and operate on an independent timing mechanism, if they brighten and fade without regard to whether the active region is in sunlight or shadow, then we're looking at something that doesn't fit the natural paradigm. Then we're forced to consider that the jets might be emissions from a technological system, that the periodicity might reflect an internal clock rather than rotation bringing surfaces into sunlight, that we might be watching something designed to pulse at precisely 16.16 hours for reasons we can only speculate about. This observation has not been made, the analysis has not been published, perhaps the data exists but hasn't been fully processed yet. Perhaps observatories have images showing the evolution of coma structure over time, but the analysis takes months and the results won't appear in journals for another year. Perhaps someone is working on exactly this question right now, preparing a paper that will definitively answer whether the jets correlate with solar illumination. We don't know. The scientific process moves at its own pace, constrained by observation opportunities, analysis time, peer review, publication schedules. But until that analysis appears, until someone publishes a comprehensive time series study showing the evolution of jet structure over multiple 16.16-hour cycles, correlated with the nucleus rotation and solar illumination geometry, mapped against the photometric brightness variations, the question remains open, suspended in uncertainty. We know the object pulses, we know the periodicity, we know the jets exist, but we don't yet know if the pulsing tracks the sun, if the mechanism is natural or something else. There's another layer to this mystery, another aspect that deepens the sense that something unusual is happening. The precision of the period itself, 16.16 hours. Not a round number, not something you'd choose if you're inventing data. It's oddly specific. 16.16. That's 16 hours and 9 minutes and 36 seconds, if you convert the decimal fraction. It's been measured across multiple rotation cycles, confirmed by independent observers using different instruments, repeating with accuracy that suggests the underlying mechanism is extraordinarily stable. Natural rotation periods can be quite stable, especially for larger objects where tidal forces and mass redistribution happen slowly. The rotation of Earth is stable to within milliseconds per century. The rotation of asteroids persists for billions of years with minimal change unless they experience a major collision or gravitational encounter that adds or removes angular momentum. But comets are different. Comets are active. They're losing mass. They're ejecting jets of material that produce torques, reaction forces that can change the rotation rate over time, speeding it up or slowing it down depending on the geometry of the jets relative to the rotation axis. The rotation period of an active comet should drift. It should vary slightly from one apparition to the next, from one perihelion passage to the next, as mass loss and jet activity alter the moment of inertia and the angular momentum. The changes might be small, fractions of a percent per orbit for a moderately active comet, but they should be measurable if you have precise enough data. Yet 16.16 hours repeats with precision. That implies stability, minimal change. The measurements taken over several weeks of observation in July and August 2025 show no detectable drift in the period. It's constant, or at least constant to within the measurement uncertainties, which are quite small given the quality of modern photometric data. For a natural comet, this stability suggests either the mass loss is extremely symmetric, distributed evenly enough around the rotation axis that it produces no net torque, or the observation time span is too short to detect the drift, which might only become apparent over months or years of continuous monitoring. But there's also the possibility that the mechanism driving the 16.16-hour periodicity isn't rotation at all, or at least not solely rotation, that something else is involved, something that maintains the period with greater stability than a rotating active nucleus would naturally exhibit. For a technological object, for something designed, precise timing is exactly what you'd expect. Engineered systems maintain precise timing. Clocks don't drift unless they're damaged or poorly designed. A spacecraft programmed to pulse every 16.16 hours would do so with precision limited only by the quality of its oscillator, its internal timekeeping mechanism, modern atomic clocks can maintain time to within nanoseconds per year. Even much cruder oscillators, simple quartz crystals, or mechanical systems can keep time to within seconds per day. If a technological artifact is pulsing, if it's following a programmed schedule, then the period would be stable. It would repeat exactly, cycle after cycle, with no drift, no variation, just perfect mechanical regularity. We can't distinguish these possibilities yet. We don't have enough data. The observations span weeks, maybe a few months at most. To detect drift in a rotation period of 16.16 hours, you'd need to observe for much longer, accumulating phase measurements over hundreds or thousands of rotation cycles, looking for small systematic deviations from a perfectly constant period. That data might exist eventually if observers continue monitoring 3I Atlas as it moves away from the sun and fades from view. But it doesn't exist yet, and by the time it might exist, the object will be too faint to observe, lost in the background noise of the distant cosmos. At any event, one conclusion is inescapable, one fact that emerges clearly from all the measurements and analyses. The reported periodicity of 16.16 hours is not directly associated with the shape of the nucleus, not caused by the rotating nucleus presenting different cross-sections to our view. The nucleus contributes too little light, less than 2% of the total, to explain brightness variations of tens of percent. The mathematics doesn't allow it. The geometry doesn't permit it. No matter how elongated the nucleus might be, no matter how much its cross-section changes as it rotates, it can't modulate the total brightness by amounts 20 or 30 times larger than its own contribution to that brightness. Instead, the periodicity must be associated with the collimated jets, with the streams of gas and dust extending from the nucleus out to distances measured in tens of thousands of kilometers, filling volumes of space larger than planets. Something about those jets is varying on a 16.16-hour cycle. The brightness of the jets, the density of material in them, the rate at which they're ejecting gas and dust, something is pulsing. And whether that variation is driven by natural rotation bringing active regions into sunlight, creating the heartbeat pattern I described earlier, or by some other mechanism we haven't yet identified, technological or otherwise, the effect is unmistakable, undeniable, confirmed by multiple independent observations. 3I Atlas has a heartbeat. That's not metaphor. That's description. The object pulses with a 16.16-hour rhythm, like a living thing, like something breathing, like a heart pumping, sending waves of material out into the surrounding space with mechanical regularity. And we don't yet know why. Let me take you deeper into the implications, into the questions this raises, because the heartbeat pattern opens avenues of investigation that extend far beyond simple mechanics, far beyond the question of whether this specific object is rotating or pulsing for other reasons. If the coma is pulsing, if tens of thousands of kilometers of gas and dust are brightening and fading in synchronized rhythm, then we're observing a large-scale dynamic process, a coordinated phenomenon spanning vast distances. This isn't just surface ice vaporizing in response to local solar heating. This is an entire atmosphere, an enormous extended structure responding to some driving force with coherence across huge volumes. And coherence at large scales requires coordination, requires some mechanism that links events happening at different locations that ensures the system responds as a whole rather than as a collection of independent pieces. In nature, coordination often arises from simple physics, from fundamental principles that impose order on complex systems. Consider the sun. Every part of its surface receives energy from the nuclear fusion reactions in the core. But different regions don't pulse independently. The sun breathes as a whole, oscillating in various modes that span the entire surface, creating patterns of expansion and contraction that are coordinated across hundreds of thousands of kilometers. The coordination comes from the fact that pressure waves travel through the solar interior, linking distant regions, allowing them to respond in unison. For 3I Atlas, the coordination mechanism could be rotation. The sun moves across the sky of the rotating nucleus, creating a traveling wave of heating and cooling that sweeps around the surface every 16.16 hours. The boundary between day and night, the terminator, moves around the nucleus as it rotates. Regions ahead of the terminator are moving into sunlight, starting to heat up. Regions behind it are moving into shadow, starting to cool down. The subsolar point, the location where the sun is directly overhead, migrates around the surface, creating a hot spot that follows a predictable path. If there is a region of enhanced volatility, a deposit of fresh ice or a vent that allows easy escape of sublimated gas, that region will produce a jet when it rotates into the subsolar region or near it. When solar heating becomes intense enough to drive vigorous sublimation, the jet turns on, material streams out, the coma brightens. As rotation carries that region away from peak solar illumination, the jet weakens. Material injection decreases. The coma dims. The coordination across the coma, the fact that brightness varies coherently rather than just showing random fluctuations from different independently varying jets, comes from the fact that there's one dominant jet, one primary source of material, and its activity is controlled by rotation, bringing it into and out of sunlight. This is elegant. It's simple. It makes sense. But there's something about the elegance that feels almost too perfect, too convenient. Consider the challenge of maintaining a coherent pulse across 25,600 kilometers. Material ejected at the start of a rotation cycle reaches that distance just as the next cycle begins. The timing works out perfectly. The periodicity of the heartbeat, 16.16 hours, matches the travel time of sublimated gas to a distance of 25,600 kilometers at the observed outflow velocity of 440 meters per second. It's as if the system knows exactly how long it takes for ejected material to reach a certain distance, and it pulses at exactly the rate required to create evenly spaced shells at that scale, like nested spheres expanding outward in lockstep. This is probably coincidence, almost certainly coincidence. The rotation period is set by the angular momentum of the nucleus, which was determined by whatever collisions and interactions shaped this object billions of years ago during the formation of its home planetary system, or during ejection events that sent it into interstellar space. The outflow velocity is set by the temperature of sublimating gas and the molecular weight of the species involved. These are independent quantities, unrelated in their origins. They just happen to have values that produce this aesthetically pleasing relationship where the period equals the distance divided by the velocity. Nature doesn't care about aesthetics. Physics doesn't optimize for pleasing relationships. Numbers fall where they fall, determined by the specific conditions and history of each object. The fact that we can write period equals distance divided by velocity and plug in the values 16.16 hours equals 25,600 kilometers divided by 440 meters per second is interesting, but not necessarily meaningful. It's a consequence of the definitions and units, not evidence of design or purpose. But when you stack the numbers, when you look at the whole picture, when you consider all the pieces together, the elegance becomes harder to dismiss as mere coincidence. A rotation period that shows minimal drift, stable to high precision over weeks of observation, an outflow velocity that happens to match observations from Webb spectroscopy and happens to synchronize with the rotation period to create coherent pulsing at scales of tens of thousands of kilometers. A coma structure dominated by collimated jets rather than isotropic emission, creating the appearance of directed beams rather than a diffuse cloud. Brightness variations large enough to be unmistakable yet precisely matched to the period of rotation. Each element is individually explainable. Each piece fits within the range of what we see in natural comets, or at least doesn't obviously violate physical laws. But together, they create a pattern that feels designed, that exhibits the kind of optimization you'd expect from engineering rather than the messy complexity you'd expect from random natural processes. And design is the concept we keep circling back to, the idea that lurks at the edge of every analysis, acknowledged in private conversations, dismissed in official reports, but never entirely absent from the discourse surrounding this object. Because if 3i Atlas is designed, if it's a technological artifact rather than a natural comet formed through accretion in a protoplanetary disk billions of years ago, then everything changes. The heartbeat isn't a consequence of solar heating and rotation. It's a signal, intentional or at least functional. The jets aren't passive sublimation driven by thermal gradients. They're emissions, controlled, directed, serving purposes we can only guess at. The precision isn't coincidence. It's engineering, the hallmark of systems designed to operate reliably, to maintain performance parameters within tight tolerances, to function as intended despite the hostile environment of interstellar space. What would a design system look like? How would it operate? These aren't idle questions. They're thought experiments that help us understand what signatures to look for, what observations would distinguish natural from artificial. If you were sending an object on an interstellar journey, if you wanted it to remain functional after millions or billions of years, in the void between stars, traveling through regions where temperatures approach absolute zero and radiation levels can sterilize unprotected materials, what design choices would you make? You'd minimize moving parts. Anything mechanical wears out, breaks down, fails eventually. You'd use passive systems wherever possible, systems that don't require active control, that function automatically in response to environmental conditions. You'd rely on rotation for stability, for attitude control, for orientation determination. A spinning object maintains its angular momentum. The axis of rotation points in a fixed direction relative to the distant stars, providing a stable reference frame. You might use rotation for power generation if you're harvesting spin, converting rotational energy into electricity through mechanisms analogous to regenerative braking in electric vehicles. You time your active systems to the rotation period. Pulsed emissions synchronize with spin conserve power, allow components to cool between pulses, reduce thermal stress, extend operational lifetime. Observations might be made when specific sensor arrays rotate into optimal orientation, when cameras or telescopes or spectroscopic instruments point in the desired direction. Course corrections would be calculated and executed at specific phases of the rotation cycle when thrusters are oriented to produce the desired change in velocity vector. A pulsing beacon synchronized to rotation makes perfect sense in this context. It conserves power by operating intermittently rather than continuously. It creates a recognizable signal, a repeating pattern that stands out against the random fluctuations of natural processes. It allows passive cooling between pulses, preventing components from overheating. It reduces the complexity of the control system because you don't need independent timekeeping beyond counting rotations. Just track the rotation. Fire the beacon every n rotations or at specific phases within each rotation. Adjust thrust every m rotations based on navigation updates. The rotation itself becomes your clock, your reference frame, your organizing principle. If the jets on 3i Atlas are emissions from such a system, If they're pulsing, not because of solar heating, but because of programmed activation cycles tied to rotation or to an internal clock that happens to match the rotation period, then the pattern we observe is exactly what we'd expect to see. Brightness variations of tens of percent as the emissions activate and deactivate, a period of 16.16 hours matching the rotation if the emissions are tied to rotational phase. Collimated jets pointing in specific directions determined by the orientation of emitters or nozzles on the object's surface. And most tellingly, jets that don't necessarily correlate with solar direction, jets that operate according to their own logic, independent of where the sun happens to be. This is why the observation I mentioned earlier is so critical, why the time series imaging showing jet behavior correlated with solar geometry is the key measurement that could resolve the ambiguity. It's the test that distinguishes natural from artificial, coincidence from design. Natural jets driven by solar heating should show clear correlation with solar illumination. They should turn on when active regions face the sun, brighten when solar flux is highest, dim when regions rotate into shadow, or when the nucleus is far from the sun and solar heating is weak. The correlation should be obvious, undeniable, precisely what you'd predict from straightforward thermophysics. Artificial emissions could point anywhere. They might point toward the sun if their purpose is to masquerade as natural sublimation, to maintain the disguise, to avoid raising questions. But they might also point in other directions if their function is communication or propulsion or observation. If the designers didn't care about mimicking natural behavior, or if they wanted the emissions to serve multiple purposes simultaneously. They might brighten and fade on a schedule unrelated to solar geometry, following internal programming rather than external forcing. The missing observation, the time series analysis that hasn't been published yet, is what we need to make this distinction. Until someone performs that analysis and publishes the results, until we can see whether the jets track the sun or operate independently, the question remains suspended between natural and artificial, between comet and craft, between chance and intention. There's another aspect worth exploring, one that takes us into more speculative territory, but remains grounded in the observational data we have. The James Webb Space Telescope, humanity's most powerful infrared observatory, performed spectroscopic analysis of 3I Atlas during its approach to the sun. Webb's capabilities are extraordinary. It can measure the composition of gases in the coma with precision that was impossible with previous instruments, identifying specific molecules, determining their abundances, even measuring isotopic ratios that reveal details about where and when the material formed. The Webb observations revealed that the coma of 3I Atlas is dominated by carbon dioxide, CO2, with a ratio of carbon dioxide to water that places this object among the most CO2-rich comets ever observed. This is unusual. Most comets are dominated by water ice. Water is the most abundant volatile in typical comets, making up 70 or 80 or even 90% of the total ice content. Carbon dioxide is present, but usually as a minor component, maybe 10 or 20% of the total volatiles. But 3I Atlas is different. The CO2 to H2O ratio is high, suggesting that carbon dioxide is the dominant ice species, that this object formed in an environment extremely cold and far from any star, where carbon dioxide ice is more stable than water ice. In the outer reaches of a protoplanetary disk, beyond the snow line where water condenses, in regions where temperatures drop below about 50 Kelvin, carbon dioxide can condense and accumulate. Objects forming in these regions would be rich in CO2, poor in water, chemically distinct from objects forming in warmer regions closer to the star. But here's what makes this relevant to the heartbeat question. to the mystery of why the jets pulse with such precision. Carbon dioxide has different sublimation properties than water. It sublimates at lower temperatures, reaches significant sublimation rates at temperatures where water ice would be nearly inert. It produces higher outflow velocities for a given temperature because CO2 molecules are lighter than H2O molecules, so they achieve higher thermal velocities. It creates different pressure dynamics in subsurface voids, where gas accumulates before erupting through vents or cracks in the surface. If 3I Atlas is rich in carbon dioxide, if that's the dominant volatile driving the jets, then the pulsing behavior could be related to specific properties of CO, 2 ice sublimation that differ from water ice behavior. Carbon dioxide can undergo what's called sublimation instability under certain conditions. The sublimation rate isn't always smoothly proportional to temperature. Instead, it can exhibit threshold behavior, nonlinear responses, where small changes in temperature cause large changes in sublimation rate. Below a certain critical temperature, sublimation is negligible. The vapor pressure is too low. Ice molecules are bound too tightly to the surface to escape in significant numbers. But as temperature crosses a threshold, sublimation rate increases rapidly, exponentially. Small additional increases in temperature produce large increases in sublimation. The system can exhibit positive feedback. Higher sublimation rates consume latent heat of sublimation, cooling the surface. But they also increase pressure in subsurface voids, which can crack the surface, exposing fresh ice, which increases the active area, which increases sublimation even more. If a pocket of CO2 ice is near this critical threshold, if its temperature hovers just below the point where sublimation becomes vigorous, then small variations in solar heating could cause large variations in sublimation rate. The ice warms slightly as it rotates into sunlight, temperature crosses the threshold, sublimation jumps from low to high, the jet ignites, gas streams out, but the sublimation consumes latent heat, cooling the ice. Temperature drops back below threshold, sublimation shuts off, the jet fades. Even though the surface continues to receive solar heating, even though it's still in sunlight, without continued sublimation removing heat, the ice begins to warm again. Temperature approaches threshold, the cycle repeats. This creates a natural oscillator, a limit cycle, in the dynamical system sense, potentially capable of producing pulsed output even from steady input. The solar heating is continuous as long as the surface faces the sun, but the response is intermittent, oscillating between active and quiescent states. If the rotation period happens to match the characteristic time scale of this feedback cycle, if 16.16 hours is close to the time it takes for the ice to warm from sublimation shutoff to threshold reactivation, you could get resonance. The system locks into a rhythm where each rotation delivers a pulse, perfectly timed, self-sustaining, stable over many cycles. The rotation sets the overall period, but the feedback dynamics determine the detailed behavior, the sharpness of the pulses, the duty cycle representing the fraction of time the jet is active versus inactive. This is highly speculative. The physics of sublimation, instability in carbon dioxide ice under cometary conditions is not well characterized. We don't have laboratory data at the relevant pressures and temperatures. We don't have detailed models of how CO2 ice behaves when it's mixed with other ices and embedded in a porous matrix of rock and carbonaceous material. The threshold temperatures, the feedback timescales, the stability of oscillating modes, all of this would require sophisticated modeling and probably dedicated laboratory experiments to evaluate properly, but it's a possible mechanism, a way that entirely natural processes could produce the precise pulsing we observe without invoking technology or design. It would explain why 3I Atlas, with its unusual CO2-rich composition, behaves differently from typical water-rich comets. It would explain the coherence of the pulsing across the large-scale coma, the synchronization that makes the entire structure brighten and fade together, and it would explain why the period is so stable, locked to the rotation by resonance, rather than just being a direct reflection of rotation bringing surfaces into sunlight. But even if this mechanism is real, even if sublimation instability can account for the heartbeat pattern, it doesn't eliminate the strangeness, doesn't make the observations less remarkable. Because resonance is rare in natural systems. Getting a natural feedback cycle to lock into exact synchronization with rotation requires fine-tuning, requires multiple conditions to be met simultaneously. The rotation period has to match the feedback timescale within some tolerance. The ice composition has to be right, CO2 dominated in the active regions. The temperature of the subsurface ice has to hover near the critical threshold for instability. The geometry has to allow stable oscillation without damping or runaway. All of these conditions have to be met at the same time in the same object. The probability of this happening by chance isn't zero. Nature is vast, and rare events happen occasionally simply because there are so many opportunities. But the probability isn't high either. And when you combine this low probability scenario with all the other unusual aspects of 3I Atlas, when you stack multiple unlikely coincidences on top of each other, you reach a point where the natural explanation starts to require as much faith as the artificial one. Either we're witnessing an extraordinarily rare configuration of natural processes, a comet that just happens to have the exact combination of composition, rotation rate, thermal properties, and structural characteristics needed to produce this specific behavior, or we're witnessing something designed to behave this way, engineered to pulse at 16.16 hours for purposes we don't yet understand. The data, as it currently exists, the observations we have access to through published papers and preliminary reports, cannot definitively distinguish between these possibilities. And that's the uncomfortable reality of studying interstellar objects, the fundamental limitation we face. We get one chance. They pass through our solar system once, following hyperbolic trajectories that carry them back into interstellar space, never to return. The observation window is limited by their trajectory, by their brightness as they approach and recede from the sun, by the capabilities of our instruments and the availability of telescope time. We gather what data we can during the brief period when they're close enough and bright enough to study in detail, and then they're gone, fading back into the darkness from which they emerged, leaving us with incomplete measurements, unresolved questions, mysteries that may never be fully solved. 3I Atlas will continue moving away from the sun. It's already past perihelion, its closest approach, already on the outbound leg of its trajectory. The coma will gradually dissipate as the object moves into colder regions of the solar system where solar heating drops and sublimation slows to negligible rates. The jets will weaken, producing less material per unit time. The brightness will decline as the object recedes. As the distance to the sun increases and the distance to Earth increases, both effects combining to make the object fainter and fainter with each passing week. Eventually, within months or at most a year or two, even our most powerful telescopes will lose track of it. The object will fade below the detection threshold, becoming too faint to distinguish from background noise, lost among the countless distant galaxies and faint stars that fill any deep image of the sky, and the opportunity to make definitive measurements will be gone. If we want to understand the heartbeat, if we want to resolve whether those jets are natural or something else, if we want to determine whether the pulsing correlates with solar geometry or operates on an independent schedule, we need to act quickly. We need coordinated observations. We need time series imaging showing the evolution of coma structure over multiple rotation periods. We need careful correlation of jet activity with solar illumination angles, with rotation phase, with the photometric brightness variations we've already detected. Some of this data has likely already been collected. Observatories don't always publish immediately. Telescope time is allocated. Observations are made. Data goes into archives. But analysis takes time, months sometimes, especially if the analysis is complex, if it requires developing new software or applying sophisticated image processing techniques. Peer review takes more time. Submit a paper to a journal, and it might be months before reviewers provide feedback. More months before revisions are completed and the paper is accepted. More months before it actually appears in print or online. It's entirely possible that somewhere right now, a research team is working on exactly the analysis needed to answer these questions, the time series study that will reveal whether the jets track solar illumination or not. Perhaps they're preparing a paper showing that the jets do indeed correlate with solar heating, brightening when active regions face the sun, fading when those regions rotate into shadow, confirming the natural explanation, putting the technological speculation to rest. Or perhaps they're finding patterns that don't fit, anomalies that deepen the mystery, jets that pulse at phases inconsistent with solar geometry, behavior that can't be explained by rotation and sublimation alone. We won't know until they publish, until the paper appears and the data becomes available for independent verification. That could be weeks from now, could be months, could be longer. The wheels of science turn slowly, constrained by the need for rigor, for verification, for consensus built through repeated independent observations and analyses. But while we wait, while the scientific process grinds forward at its deliberate pace, the data we do have keeps whispering the same message, the same pattern that won't quite resolve into certainty. 3I Atlas is pulsing. The light varies by tens of percent every 16.16 hours. The coma, not the nucleus, is the source of most of that variation. Jets of gas and dust are involved, collimated streams extending tens of thousands of kilometers from the core, organized structure rather than random diffusion. And the simplest explanation, the one we'd prefer to believe because it fits within the framework of what we already know, that rotation-driven solar heating of asymmetric volatile deposits causes the pulsing, doesn't quite account for the magnitude of the effect. The nucleus is too small. It contributes too little light, even allowing for the most favorable geometric configurations, even assuming the most elongated possible shape and the most asymmetric distribution of surface brightness. The rotation of the nucleus cannot produce 20 to 40% variations in the total light when the nucleus itself only contributes 2% or less of that total. Something more is happening. Something that makes this object different from typical comets, different from the other interstellar visitors we've detected, different in ways we're still struggling to understand, still trying to fit into our existing frameworks of explanation. And so the mystery persists. The heartbeat continues every 16.16 hours with precision that seems almost mocking in its regularity. 3I Atlas brightens and dims. The jets pulse. The coma breathes. Somewhere in that vast cloud of gas and dust surrounding a small icy nucleus a few kilometers across, processes are occurring that we observe but cannot yet fully explain. The photons that reach our telescopes, that strike our detectors, that get converted into electronic signals and stored as data files, those photons carry information. They tell us about brightness, about wavelength, about polarization, about all the physical properties we can extract from electromagnetic radiation. But information is not the same as understanding. We can measure the periodicity with extraordinary precision. We can calculate the fraction of light from nucleus versus coma with confidence based on Hubble's images. We can image the jet structures and track their apparent motion across the sky as the object moves through our solar system. We can measure the chemical composition with Webb spectrographs and determine that CO2 dominates. All of this is information, hard data, reproducible measurements that different observers confirm, but we cannot yet say with certainty what drives the pattern, what mechanism produces this regular pulsing, whether we're witnessing pure physics operating according to laws we understand or something more, something that challenges our categories, something that doesn't fit neatly into the box labeled natural comet or technological artifact, but sits uncomfortably between them, resisting classification. And so we watch. We continue observing as long as the object remains bright enough to study. We refine our measurements. We develop new models and test them against the data. We publish papers presenting our findings and debating their interpretations. We plan follow-up observations using different instruments, different techniques, searching for the key piece of evidence that will tip the balance toward one explanation or another. This is how science advances, how mysteries gradually yield to understanding through patient accumulation of evidence and careful application of reason. But sometimes, rarely, the mystery doesn't resolve. Sometimes the evidence points in multiple directions. Sometimes the universe presents us with phenomena that fit more than one explanation equally well, that remain fundamentally ambiguous despite our best efforts to clarify them. And in those cases, the scientific method requires us to acknowledge the ambiguity, to present multiple hypotheses, to avoid premature conclusions, to remain open to surprising answers, even when they make us uncomfortable. 3I Atlas may be such a case. The heartbeat is real, confirmed by data from multiple independent sources. The periodicity is precise, 16.16 hours repeating with minimal detectable drift. The jets exist and pulse, creating brightness variations larger than the rotating nucleus can account for. But whether this is natural sublimation instability in CO2, rich ice synchronized with rotation through resonance, whether it's simple rotation, bringing unusually active regions into sunlight in a manner we haven't quite modeled correctly, whether it's emissions from a technological system operating on a programmed schedule, or whether it's something else entirely that we haven't imagined yet, the data does not yet tell us. And perhaps it never will. Perhaps 3I Atlas will fade into the distance, beyond the reach of our instruments, its secrets intact, leaving behind only measurements and speculation, and that haunting 16.16-hour pulse echoing in the datasets, a reminder of the day we detected something from another star system and couldn't quite determine what it was. What we're left with, what remains after all the analysis and debate, is wonder. Not the comfortable wonder of understanding, the satisfaction that comes from solving a puzzle and seeing how all the pieces fit together, but the deeper wonder of mystery, the recognition that the universe is larger than our theories, more complex than our models, full of phenomena that challenge our categories and resist our explanations. This is the wonder that drives exploration, that motivates the building of larger telescopes and more sensitive instruments, the development of new analysis techniques and theoretical frameworks. This is what keeps us looking up at the night sky, keeps us asking questions even when the answers are elusive, keeps us searching for understanding even when the universe seems determined to maintain its secrets. In the history of astronomy, there have been moments when a single observation changed everything, when one measurement or discovery forced a complete reevaluation of our place in the cosmos. When Galileo pointed his telescope at Jupiter and saw moons orbiting another planet, the Earth-centered universe collapsed. The revelation that we weren't the center of everything, that other worlds had their own satellites, shattered millennia of philosophical certainty. When Edwin Hubble measured the redshift of distant galaxies and found that they're all moving away from us, that the universe is expanding, the static eternal cosmos transformed into something dynamic, evolving, with a beginning and perhaps an end. The discovery of cosmic expansion fundamentally changed how we think about space and time. when the first exoplanet was confirmed orbiting another sun-like star, when we detected the slight wobble in the star's motion caused by an orbiting companion, the uniqueness of our solar system dissolved. We realized planetary systems are common, that worlds beyond our own fill the galaxy, that the building blocks of planets are everywhere, and the processes that form them operate around countless stars. Perhaps 3i Atlas will be remembered as another such moment. Another observation that forced a paradigm shift. The object that made us confront the reality that interstellar space isn't an empty void, but a medium through which objects travel, carrying information, and perhaps carrying technology from one star system to another. The comet that pulsed with such precision that we couldn't ignore the possibility of design, couldn't simply wave away the questions about artificial versus natural. The visitor that arrived from the darkness and left us questioning everything we thought we knew about being alone. Or perhaps it will be a footnote, a minor entry in the catalog of interstellar objects, an unusual comet with interesting properties that were eventually explained through refined understanding of sublimation physics and rotation dynamics. A natural object that mimicked artificial characteristics closely enough to spark debate, but ultimately revealed itself as just another example of how strange nature can be. When we look closely enough, how the universe continues to surprise us with configurations we hadn't anticipated. Either way, the fact that we're here now, able to observe this object, able to measure its heartbeat, able to ask these questions, is itself extraordinary. We are living in the first era of human history, where we have the technology to detect interstellar visitors, to study them in detail, to contemplate their implications. Our grandparents didn't have this capability. When the first interstellar object was detected in 2017, when Oumuamua swept through our solar system and astronomers scrambled to observe it before it faded, that was a first in all of human history. Never before had we knowingly observed an object from another star system. Now we've detected 3: Oumuamua, 2i, Borisov, and 3i Atlas. Each one different, each one strange in its own way, each one forcing us to expand our understanding of what's out there in the galaxy, what kinds of objects wander the void between stars, how common these encounters might be. And that means we have a responsibility, an obligation to look as carefully as possible, to gather the best data we can, to consider all explanations honestly, and to follow the evidence wherever it leads, even if it leads to conclusions we find uncomfortable or unlikely. Because this might be the closest we ever come to detecting evidence of technology from another civilization. Or it might be a beautiful example of exotic natural physics that we'll study for decades to come. We don't know yet, but we owe it to ourselves, to our descendants, to future generations who will look back on this moment and judge whether we rose to the occasion, to investigate thoroughly, to question carefully, to remain open to possibilities we haven't yet imagined. The universe is vast. The galaxy contains hundreds of billions of stars. We now know that most of those stars have planets. The Kepler mission taught us that. Planetary systems are common. Rocky worlds exist around many stars. Some fraction of those worlds orbit in the habitable zone where temperatures allow liquid water. Some fraction might harbor life. Some fraction of that life may have developed intelligence. Some fraction of intelligent species may have developed technology. The numbers are uncertain. The Drake equation, which attempts to estimate the number of communicating civilizations in the galaxy, has terms we can barely constrain. We don't know the probability that life arises on a habitable planet. We don't know the probability that life develops intelligence. We don't know how long technological civilizations typically survive before destroying themselves or transcending into something we wouldn't recognize. But even conservative estimates, even if you plug in pessimistic values for all the uncertain terms, suggest we're not likely to be alone. The galaxy is too big. The number of opportunities is too large. Intelligence has probably arisen elsewhere. Technology has probably been developed by others. And if that's true, if civilizations exist elsewhere in the galaxy, then eventually, inevitably, we might encounter evidence of their existence. That evidence might come as a radio signal, carefully constructed to be recognizable as artificial, carrying information encoded in mathematical sequences or modulated patterns. It might come as a laser pulse, a brief flash of coherent light from a distant star system, perhaps part of an interstellar communication network. It might come as an anomaly in exoplanet transit data, something that suggests megastructures rather than natural planets, Dyson swarms or orbital rings or other engineering on scales we can barely conceive. Or it might come as a comet, an object passing through our solar system, looking mostly natural, behaving largely as we'd expect from sublimating ice and rotating rock, but with just enough strangeness to make us question, to make us wonder, to make us look more closely. And when we look closely, we might see a pattern, a pulse, a heartbeat, regular, precise, unexplained by the simple physics we thought applied. 3I Atlas is pulsing. That's a fact, confirmed by observations, reproducible, undeniable. The interpretation is uncertain, still debated, still under investigation. The implications are profound, reaching into questions about whether we're alone, about whether technology from other civilizations visits our solar system, about whether the cosmos is filled with silent watchers or whether we truly are unique. And as the object continues its journey outward, as it fades from view and eventually becomes undetectable, even to our most powerful instruments, it leaves behind that most precious gift that any mystery can offer, a question that demands an answer, a puzzle that motivates continued investigation, a reminder that we still have so much to learn about the universe we inhabit. The heartbeat continues every 16.16 hours, regular as clockwork, precise as mathematics, beautiful as poetry, and utterly, fascinatingly unexplained. We are watching the sky. We are measuring the light. We are asking questions and seeking answers. And somewhere in the darkness between the stars, other objects may be traveling, other visitors may be approaching, other mysteries waiting to be discovered. Because the universe is not static, it's dynamic, evolving, full of motion and change and surprises. Objects cross the vast distances between stars. Comets are ejected from planetary systems and wander the galaxy for eons. And every so often, one of them passes close enough to our sun that we can see it, study it, wonder about it. The next interstellar visitor is already on its way. It might arrive next year, or in a decade, or in a century, but it will arrive. And when it does, we'll be watching, we'll be measuring. We'll be asking the same questions we're asking now about 3I Atlas. Is it natural? Is it design? What can it tell us about the galaxy beyond our small corner of space? What secrets does it carry from the stellar system where it was born or the civilization that might have built it? These questions connect us to something larger than ourselves, larger than our planet, larger than our solar system. They connect us to the cosmic community, to the possibility that we share this galaxy with others, that intelligence has arisen in multiple places, that the universe is not just matter and energy, but also mind, consciousness contemplating itself, reaching out across the light years, seeking contact, or at least seeking knowledge. And whether 3I Atlas is a messenger from that cosmic community, whether it carries within it technology designed by minds we've never met, or whether it's simply a chunk of ice and rock following the laws of physics without purpose or intention, it has already given us something valuable. It has given us a moment of wonder, a reason to look up, a reminder that the universe is full of surprises, that our current understanding is incomplete, that mysteries remain to be solved. In a world often dominated by the mundane and the familiar, by routine and predictability, by the endless cycle of daily concerns and immediate problems, that gift is precious beyond measure. It reminds us that we're part of something vast, something ancient, something that existed long before us and will continue long after we're gone. It reminds us to look beyond our small concerns to the larger questions, to wonder about our place in the cosmos, to ask whether we're alone or accompanied on this cosmic journey. So as you drift towards sleep tonight, as your consciousness gradually releases its grip on the immediate and the urgent, as your mind begins to wander and thoughts become less structured, less bound by the demands of logic and reason, let yourself think about 3I Atlas out there in the darkness. Imagine it tumbling through space, pulsing with its 16.1 6-hour rhythm, carrying within it secrets we may never fully uncover. Picture the jets of gas extending thousands of kilometers into the vacuum, glowing faintly as they scatter sunlight, breathing in and out like a living thing, though whether that life is chemical or mechanical or something else entirely remains an open question. And know that you are part of this story. You, lying here in comfort, safe and warm, contemplating these mysteries from the surface of a small rocky planet orbiting an average star in an unremarkable region of a spiral galaxy, are connected through chains of photons and mathematics and shared curiosity to that distant visitor. The same laws of physics that govern the heartbeat of 3I Atlas govern your heartbeat. The rhythm of neurons firing in your brain as you process these thoughts, the dance of atoms and molecules that constitutes your existence. We are all made of star stuff. As Carl Sagan reminded us decades ago, the atoms in your body were forged in the nuclear furnaces of stars that lived and died billions of years ago, before our sun existed, before Earth formed. Those atoms were scattered through space in supernova explosions and stellar winds. They drifted through interstellar clouds. They were swept up in the gravitational collapse that formed our solar system. They accreted into planets. They were organized into complex molecules. They became part of living organisms. They became you. In that sense, we are all interstellar travelers. Our atoms have journeyed across light years, across eons, from their birthplaces in stellar cores to their current arrangement in your body, in your mind, in the consciousness that's contemplating these words right now. The universe contemplating itself through human awareness, through scientific investigation, through the patient accumulation of observations and the careful construction of explanations. 3I Atlas pulses in the darkness, maintaining its 16.1 6-hour rhythm, indifferent to our observations, unconcerned with our interpretations, simply being what it is, whether we watch or not. You pulse too, your heart maintaining its own rhythm, marking time, keeping you alive, connecting you to the fundamental oscillations that run through all of nature, from the vibrations of atoms to the orbits of planets, to the pulses of neutron stars, to the expansion of the universe itself. And somewhere in the vast conceptual space between your heartbeat and the heartbeat of an interstellar visitor, in the resonance between human wonder and cosmic mystery, lies something essential about what makes us human: the capacity to look beyond ourselves, the ability to ask questions that may not have easy answers, the drive to seek understanding even when the universe offers only ambiguity, the willingness to contemplate possibilities that challenge our assumptions and expand our imagination. Sleep well, knowing that the mysteries continue, that the observations proceed, that somewhere right now telescopes are pointing at distant objects, gathering photons, recording data, slowly building the archive of measurements that will eventually, perhaps, tell us whether we are alone or accompanied on this cosmic journey through space and time. The answer, whatever it turns out to be, will not diminish the wonder. It will only deepen it, opening new questions, revealing new mysteries, showing us that each answer we find leads to more questions, that understanding is not a destination but a journey, that the universe will continue to surprise us as long as we keep looking. The heartbeat continues. 16.16 hours. Regular as clockwork. Precise as mathematics. Beautiful as poetry. Mysterious as the cosmos itself. And whether it's the pulse of sublimating ice driven by rotation and sunlight, or the signal of something designed, something sent, something intended, it reminds us that we live in an age of wonders, an era when we can detect visitors from other star systems and contemplate their nature, when we can measure the universe with unprecedented precision and still find ourselves confronted by questions we cannot yet answer. Keep looking up, keep asking questions, keep wondering, because the universe is speaking in the language of light and matter and motion, in the patterns that repeat and the anomalies that don't fit, in the data that confirms our theories and the observations that challenge them. And if we listen carefully enough, if we observe patiently enough, if we remain open to possibilities we haven't yet imagined, we might just hear what it has to say. We might just glimpse the answers to questions humanity has asked since we first looked at the stars and wondered what they are, where they came from, whether anyone else out there is looking back at us and wondering the same things. The heartbeat of 3I Atlas echoes across the solar system. And in that echo, in that precise 16.16 hour pulse, we hear the voice of the cosmos asking us to listen more carefully, to look more closely, to think more deeply about our place in this vast, incomprehensible, magnificent universe we call home. Clear skies and good night.